How we doing?
Good. We doing good. I'm doing good.
What questions do you have before we get going? No questions? We're good? All right, so don't forget to email me whether you're going to take the exam at our usual time on Friday or if you're going to take it on Monday instead. Okay, just let me know. Yes.
So with the say we were taking on Friday, could we class us not because
Yeah. Yep. Yeah. You can still come in at 8. Yeah, absolutely. Yep. Yeah, I'm planning on still starting at 8, like we did have it done. Yep. But just shoot me an email and let me know. Yep. Which one you prefer? Because I know several people are going to be gone this week, so I figured might as well give everybody the opportunity to take it later if they'd like to. So, all right. So last thing we talked about on whatever day that was, Monday. Today's Wednesday, right? So on Monday we talked about the rank and nullity of a transformation. So we said that the rank is the dimension of the range, and the nullity is the dimension of the kernel. Remember, your range corresponded to the column space of your standard matrix for the transformation, and the nullity corresponds the kernel corresponds to the null space. So we've got that rank nullity idea for matrices, and then we also have the rank nullity idea for transformations. And remember that it turns out that your rank plus your nullity for matrices is the number of columns in the matrix. The columns of the matrix turn out, for your standard matrix for a transformation, turn out to be corresponding to your input space, your domain. So the rank plus the nullity turns out to be the dimension of the V, your domain. Okay. So let's look at these examples that we have at the bottom here. It asks you to find the nullity of each of the transformations. It tells you that the transformation has rank 3. So what's the nullity going to be for part A? It'll be 2, right? If it has a rank 3, the dimension of your domain is 5 here, right? So the nullity has to be 2. And that makes, if you think about it, that makes sense from a matrix standpoint, right? If I did the standard matrix for that transformation, doesn't matter what it is, but if I did the standard matrix for that transformation in part A, what would the size of the matrix be? 7 by 5, right? So if it has rank 3, that means we would have 3 pivots when we row reduce. That would give us 2 pivot less columns. So the nullity would have to be 2 in that case, right? Because we only get 5 columns in our matrix. What about the next one? In part B, you're told that the rank is 1. So what would your nullity be in this case? Yeah, it's going to be 4 in this case, right? Because why? Remember what the dimension of this one is? It's 5, right? It's P4 in this case, right? A little bit trickier. Okay. All right. So the dimension of your P4 is 5, so that's why the nullity has to take up the rest of the spots, if you will. Yep, for your nullities, it would be the domain. Yeah, whatever the dimension of the domain is minus the rank. Yeah, that's right. Okay. Yes. Well, what's the domain? What's the dimension of your domain in this case? 5. And if the rank is 1, rank plus nullity has to be dimension of domain. 5 minus 1 is 4. Right. This is the formula we're using here. Right. If a rank is 1 and your dimension of your domain is 5, what fills in the blank? 4. Yeah, that's why it's 4. Yeah, because what was the dimension? What's the dimension of this one? 5, and the rank was 3. Okay. So in C, the range is R3. If the range is all of R3, by the way, that would tell you what about the transformation? What word do we use if the codomain is the same as the range? Onto, right? So that would tell you it's onto, correct? If it's an onto transformation, what has to be true about your reduced row echelon form of the standard matrix? Okay, yeah, so if it's going to be onto, we need to make sure that we can always solve the equation, right? Right, remember that if it's onto it, it'll solve the equation. If we always can solve it, it have a pivot in every row, right? For it to be onto, so it'd be a pivot in every row. Pivot in every column would tell you what instead? Not onto, but 1 to 1, right? Pivot in every column is 1 to 1. Pivot in every row is onto. Okay. And then the one that kind of has that same idea with the linearly independent and spanning ideas, right? Okay. In any event, if it's onto in this case, what would the rank of this transformation be? It has to be 3, right? Because remember, the rank is the dimension of the range. The range is all of R3. Dimension of R3 here is 3, right? Okay, so the dimensions, to write it this way, the dimension of the range is 3. Since the range is all of R3, so that tells you that the rank of the transformation is 3. Oops. So what does that tell you about the nullity? It's 3 because that's to fill it up, right? Yeah. And then finally, the last one. The last one just tells you the dimension of the range is 3. So that tells you the rank is what? 3. What's the dimension of your domain in this case? 4. So the nullity has to be 1. Yeah, let's phrase something this way. If the nullity is 0, what does that tell you about the transformation? If the nullity is 0, it tells you what? It's 1 to 1, right? Good. Because there wouldn't be any free variables in that case, right? Because if the dimension is 0, the only space that has dimension 0 is the space that just has the 0 vector in it. That's the only one that has dimension 0. M22 is 2 by 2 matrices, so yeah. So remember, you multiply those two numbers together to get you the dimension. So if it's m sub mn, you would do m times n to get the dimension. Yep. All right. So let's ask this. More examples with rank and nullity. What's the dimension of your input space in this case? 12, right? What's the dimension of the output space? 10, okay? So if we were creating the standard matrix for this transformation, what would be the size of that standard matrix? It would be a 10 by 12, right? If you row reduce a 10 by 12 matrix, at least how many pivotless columns do you have to have? 2, right? So going back to this question now, what's the smallest possible value for the nullity? It'll be 2, right? Okay. So let's think about it with the dimension, the rank and the rank and nullity equation, the rank nullity equation. So remember, the rank plus the nullity is the dimension of your input, right? Dimension of the input space, right? When your t go, if I take my t going from V to W. So in this case, the dimension is 12, right? We agree? And then these two things have to balance, right? Balance each other out to get to the 12. They have to balance out that 12. What's the very, very biggest that this rank part could be? Well, the biggest it can be is if your transformation is onto, right? Right? So the rank has to be less than or equal to 10 because that's the dimension of the output space in this case. If everything has to balance and make it up to 12, then your nullity has to be at least 2. Right? Because when I add them together, I have to get 12 in this case. I have to get the dimension of the input space. The biggest the rank can get is 10 because that's what the output space it would be onto in that case, right? I can't get bigger than 10 for the dimension of the output, the dimension of the range, I mean. So if the rank is less than or equal to 10, the nullity has to be at least 2. So you can think about it a couple of different ways, right? Think about the matrix idea or think about your rank nullity equation, either or. Yes. Say it again. Well, it depends on the transformation. The rank and the nullity will depend on what the transformation is. This just gives you bounds on what it has to be. It could be 9 and 3. It could be 8 and 4. Yes. Well, okay. So the rank. Do you understand why the rank can't be any bigger than 10? Well, when I add the rank and the nullity together, I have to get 12 in this example. Yeah. So if this big as this is can get us 10, the least this can get us 2. It has to be at least 2. And if the rank is smaller, that one has to be bigger to balance it. Okay. All right, same idea in the next one here. Except we're going to go with rank versus nullity. Again, let's think about it from a matrix perspective because we're used to matrices. If you were to create the standard matrix for this transformation, what size would the matrix have? 10 by 6, right? So again, rank is still number of pivots when we do the reduced row echelon form, right? So what's the maximum number of pivots you could possibly get? It's 10 by 6, it's 6, isn't it? Because remember, you can't repeat a pivot in any column or any row, right? So you run out of columns by the time you get to 6, right? So what would be the biggest rank you could possibly have then in that case? 6. So could any transformation from M23 to R10 ever be onto in that case? No. Because the highest the rank can get is 6. It can't get to 10, right? All right, so let's go back to the rank nullity equation and see if we can do the same argument. So again, rank plus nullity is dimension of your input. And I'm always using the V for the input here. We just said that this is 6, right? Right? So in particular, what's the biggest either of these two numbers could possibly get? 6, right? We can't get any bigger than 6 because I'm adding those two things together, right? So your rank always has to be less than or equal to 6. Okay. All right. So this leads us into the next example here to try to summarize these things. But notice that if you're in the first case, the dimension of the domain was bigger than the dimension of the range. And we just said it couldn't possibly be 1-to-1, essentially, right? Because the nullity always had to be at least 2. And you told me earlier that if it's 1-to-1, the nullity has to be 0. Okay? So no transformation there could possibly be 1-to-1. Here, no transformation could possibly be onto. So let's look at this next example. I'm telling you what the standard matrix is, or at least what the size of the standard matrix is. It says it's 6 by 4. If it's a 6 by 4, what's the dimension of your domain? Let's just use T going from V to W just for the notation. What's the dimension of V? 4, good. The dimension of W? 6, good. Okay. That answers the first two questions, right? Everybody understand why? Because remember it flip-flops it? No? Don't understand why?
You said it flip-flops.
It flip-flops your dimensions, right? So remember that if we think about it in terms of coordinates, if I'm in remember that the way we make our matrix, you would, try it this way. When we did our standard matrix, remember we always did put our basis vectors in and then the coordinates that way. Erase that. You put your basis vectors in the transformation and find the coordinates and then put them down this way. Right, to find your matrix. This would have the same number of coordinates as whatever was in your output space, your codomain. Okay, so the number of rows corresponds to the dimension of your output space. The number of columns corresponds to how many basis vectors you plugged in for your inputs. So that's why it's 4. That's why it gets flip-flopped. So input is the second dimension, output is the first dimension for your matrix. Yes?
So like I'm gonna try to find the rows of coordinates.
Yeah, it always flip-flops, yep. Always, yep. Because again, what we're trying to do is we're trying to replace it with matrix multiplication, right? So if I have my standard matrix here, and I have my vector written this way, then I would have whatever the dimension is for the input space, right? The number of coordinates here is the dimension of whatever the input space is. So my columns here have to match to make my matrix multiplication work. So that's why the number of columns is the dimension of your input. Because I have to make the matrix multiplication work, right? The coordinates here is how many things are in your basis. Okay. So my columns have to match with that. That's why it ends up being flip-flopped. Okay. All right. So let's answer these two questions. Which of these two things can it be? Can it be 1-to-1 or can it be onto? It can be 1-to-1, right? But it cannot be onto. Why can't it be onto? Yeah, they can't get a pivot in every row in this case, right? They're not going to have enough rows. Because if we have 6 rows, we couldn't possibly get a pivot in every row, right? Okay. But your dimension of your codomain is greater than the dimension of the domain. So that tells you it can't be onto. Okay. All the time, yeah. All the time. Yep. Every single time. That's the whole point why we're doing this. Yep. Your input space is too small. It cannot possibly be 1-to-1. All the time. All right. So, my goodness. So, in particular, we know that the rank of this transformation is less than or equal to what, no matter what? 4, right? It's always going to be less than or equal to your input space. However, your nullity, could be 1-to-1. So all I can really say about the nullity is it's greater than or equal to 0. It also has to be less than or equal to 4. But in particular, it could be 1-to-1. Could be one. Does it have to be 1-to-1? No. Could be. It's allowed to be, but we know for a fact it cannot be onto. Yeah. How can it be nullity? If it's 1-to-1, the nullity will be 0. Right? It can be 1-to-1. Yeah, there's nothing stopping it from being 1-to-1. The dimension of your output space is big enough. Okay. Let's look at the next one. What's the dimension of your domain? 13. The dimension of your codomain? 8. Can it be 1-to-1? No. The input space is too big. In particular, your nullity is always going to be greater than or equal to what? 5, yeah. Right? Because what does your rank have to be less than or equal to? 8, right? Remember, your rank is the dimension of the range. Where does the range live? In the domain or in the codomain? Codomain, right? So the range can't get any bigger than your codomain, right? So your rank can't be any bigger than the dimension of your codomain. So your rank is always less than or equal to 8, no matter what. If your rank's less than or equal to 8, and your domain has dimension 13, then your nullity has to be at least 5. Remember, you get the rank plus the nullity has to be the dimension of the input, right? Let me write down that sum again, right? Rank of the transformation plus the nullity of the transformation has to be the dimension of your input, which in this case is 13, right? If this is less than or equal to 8, so if this can't get any bigger than 8, what do you have to say about this term in your sum? It can't be any less than 5, right? Right? You have no choice. It has to fill it up, right? It has to balance. I have to have 13 when I'm done. If one drops below 8, the other one's going to go above 5. The other one can't get any higher than 8, so this has to be at least 5, right? Okay. So in particular, can it be 1-to-1? No, it can't be 1-to-1. So if your dimension of your input is greater than the dimension of the output space, it can't be 1-to-1, and that's all the time. Just in case they wanted to ask me that one again. That one's an all the time one as well. Okay. These look like good true-false questions, by the way. Just as maybe a little bit of a precursor for the exam. These look like good true-false questions. Okay. Can it be onto? Yes. Does it have to be onto? No. Good. Like I said, these look like good true-false questions. Okay. They're good concept true-false questions. All right. Questions on that at all? All right. The last thing in this section, I talk about isomorphism. Literally means isomorphism means same structure. Iso is same, morphism is structure. Okay, so isomorphism literally means they have the same structure. From a linear algebra perspective, we say something is a transformation if the transformation is both 1-to-1 and onto. If you've heard the word before, that we refer to that type of a function as a bijection. 1-to-1 and onto is a bijection. 1-to-1 is injection. Onto is surjection. Injection and surjection together gives you bijection. Okay. So again, isomorphism literally means same structure. So what do I mean by that? We've talked about basically treating some things as the same structure before. P2 is your set of polynomials of degree less than or equal to 2 plus the 0 vector. How do you typically write a second degree polynomial? Yeah, an ax squared plus a bx plus a c, right? That's typically how it gets written. How do you add polynomials? You combine like terms, right? You add here, you add here, you add here, correct? Do we combine those when we add? No, we add them in separate components, don't we? Right? How do you do a scalar multiple? You distribute it through, don't you? You distribute it to each component. What does that behave like? What other structure does that behave like? I might as well have written it that way, right? If all I'm going to do is just add like terms or add components, I might as well do it that way, right? What does that look like? It looks like R3, doesn't it? So in particular, as vector spaces, R3 and P2 are isomorphic. They have the same structure. Why? Because I add exactly the same and I do scalar multiples exactly the same. I might treat them as separate objects. One's a polynomial, one's a three-dimensional vector. But the way addition and scalar multiplication work is exactly the same. That's why they're isomorphic. Okay? In particular, if you did your transformation from R3 to P2, where you did T of A, B, C equals AX squared plus BX plus C, that's 1-to-1 and onto. Okay? That would be your linear transformation, and you can show it's a linear transformation. Okay? That's what it means to have the same structure. Their addition and scalar multiplication is essentially the same thing. So you really didn't do anything different. You're just calling them different names. Okay. All right. We can tell easily if two finite dimensional vector spaces, so all finite dimensional means is that the space has a finite basis. Remember, dimension is just number of elements in a basis. So finite dimensional just means there's a finite basis. Okay. We can tell easily if two spaces are isomorphic. It's just if and only if they have the same dimension. That's all you need. If the two spaces have the same dimension, meaning they each have a basis that has the same size, then they're automatically isomorphic. Period. Okay. The reason for that is, just to show you real quick, I'm not going to go through a whole proof. Say this is a basis for your input space and a basis for your output space. Can you tell me what a 1-to-1 function might be from just those two sets? Can you tell me how to map one set to the other that's 1-to-1 and onto? Yeah, just take B sub I and map it to C sub I, right? Now remember, what did we say about transformations? If you know what a transformation does to a basis, then we know completely what the transformation does, right? Right? As soon as I write that, I've completely determined what the transformation is. Right? Because remember, why do we like bases? Because we can write everything as a linear combination, right? Oh, I put my hat on the wrong spot. Let's say I had a linear combination of my basis vectors for my input. What can I do? What was the whole point of this? Why did we care about basis vectors so much with transformations? What can I do? With respect to the sum, what can you do? Break it up and then do what? Pull up the constants, right? We've talked about this before, haven't we? Right? Once I know what the transformation does, I know what it does to the basis. I know what it does completely, correct? That's the whole point of this. And so you'd have K1, C1 all the way out to Kn, Cn. All I've done is, what have I done? I've corresponded linear combinations of this basis in my input space with linear combinations of this vector in my output space, right? This is essentially an arbitrary vector in my input space. I've done a correspondence with that with an arbitrary vector in my output space. I have a nice one-to-one and onto function now. So they have to be identical. They have to be not identical, but isomorphic as spaces. That's the whole point. And again, this just illustrates the point of once you know what a transformation does to a basis, you know what the transformation does, period. That's the whole point of bases, right? Okay. All right, so let's just see if we can, like I said, I'm not going to go through a formal proof. I mean, that's pretty much is the proof, okay? All right, that pretty much is it. All right, so let's see if we can think of some examples that are isomorphic to, say, R6. Dimension of R6 is 6. So can you think of some spaces that have the same dimension? P5 works, good. Can you think of another one? M23. Can you think of another one? M32. All of those would be isomorphic, right? As long as you know that the dimension is 6, you know what it is. You're done. That is it. Anything that has dimension 6 is isomorphic to R6. Does that make sense? And again, think about why. How do you add polynomials? You add like terms, so you might as well just be adding in the coordinates of the corresponding vector, right? How do you add matrices? Entry by entry, so you might as well just think about them as a big, long, 6-dimensional vector. Okay. That's the idea. All right. Okay, so that will be what we'll stop for test things. So I'm going to talk about some new things today. It's just an extension, but this won't be on this exam. Okay. All right. Same concept, just extended. All right. All right. So we've already talked about how to create a standard matrix for a linear transformation, right? Put in the standard basis, figure out the outputs for your standard basis, and make those in as columns, right? We can do this for any basis that we're given. Doesn't have to be the standard basis. Okay? All right, so here's how we do that. Here we've got vectors for my basis vectors for my input space. Here we have basis vectors for my output space. What's the dimension of your input space? Given what I gave you, what's the dimension of the input space? The n, right? Because there's n vectors in that basis. Dimension of the output space? M, right? Because there's m vectors. If I'm going to create a matrix, what size matrix do you think we're going to end up with? M by n. Yeah, exactly, the same idea, right? And we're going to create it the same way. Okay? The notation looks a little goofy. It looks like I flip-flopped the b and the b prime, but why? Remember what happens? We had dimension n to dimension m. It's m by n, right? They're flipped, so that's why it looks flipped on the notation. Okay. All right, here's what you do. Same idea. We're going to take the basis vectors, and we're going to plug them in to the transformation, and we're going to put them in as columns. Now, here's the issue. Oops, those are not my vectors. I use V's, not B's. Sorry. Okay. Here's the issue, though. I don't know that I have necessarily Rn vectors, right? I don't know that I'm going to get just coordinates out, right? So for each of the outputs, I've got to figure out what the coordinates are relative to the basis that we have. Okay. And then put those in as columns. So let's do this with an example. I think it's a little bit more illustrative with an example than writing down the definition this way. Okay. All right. So first example we have here, our transformation is going from R2 to R3. How do I know it's going from R2 to R3? No, I've got a two-dimensional input vector here and a three-dimensional output vector here, right? So it's going from R2 to R3. What size matrix will we end up with when we're done? 3 by 2, right? Right? Good. All right, so here's how we do this. The first thing you want to do is you want to plug in your basis vectors into the transformation. Yes? Say it again. No, that's from R2 to R3 because that says that's input and input. Right? The input and output, right? It says a two-dimensional input and a three-dimensional output. And my basis here is a two-dimensional vector and three-dimensional vectors and three-dimensional vectors. So it's going from R2 to R3. It's just the matrix will be 3 by 2. All right. So first thing we're going to do, just like we did before, figure out what the outputs are for the basis vectors. What did we do before? We just did the standard basis, right? Now we've got a non-standard basis. We're just going to put in a different set of vectors. Okay. What do you get when you put in 1, 3?
7, 8, 1, 0.
Good. What do you get when you put in negative 2, 4? Get positive 2. Don't we have in 0? Okay, good. That's the first step. First step should be the easy step. Okay? Take your basis vectors and plug them in. That should be should be an easy step, right? The next step is a little bit uglier. I need to find, now ordinarily we would have just taken these outputs and put them in as columns, right? But that would assume that these are the outputs relative to the standard basis, right? Those are the coordinates relative to the standard basis. I need the coordinates of these relative to the basis we're given. Okay, how do we find those? So again, we need the coordinates with respect to E prime. How do we find those? Yeah, set them as a matrix and row reduce, right? I need a linear combination of these 3 vectors that give me each of those, right? That's what I need, right? I might as well be fancy about it and do it all at once, okay? So here are my basis vectors. I'm going to just go augment so that I would make an augmented matrix, right? I'll put 7, negative 1, 0 in that first column, that next column, and 6, 2, 0 in the last column. And then we want to row reduce. If somebody wants to type that in. I bet I know what the first part's going to look like. By the way, you should know what the last one's going to be. If I want a linear combination of these 3 vectors that gives me either of those 2 things, can I use this first vector at all? Not at all, can I? Why not? Good. The other 2 vectors have a 0 in there, and this would be a non-zero if I use it, right? So what's your first constant going to have to be? 0, right? So you should end up with, when you row reduce, you should end up with a 0 here and a 0 here, right? This is don't use the first vector at all. What do you get for the other 2 or other 4 entries? Negative 1? Is that what you said?
Negative 1/2.
Oh, okay. Sorry. And a 1? 2.6? 8 thirds? Okay. 4 thirds. Okay, cool. That's just using your calculator and row reducing, right? Okay. All right, so when I have the matrix, or excuse me, the vector 7, 1, 0, and I want its coordinates relative to B prime, 7, 1, 0 was that first one there, so the coordinates would be 0, negative 1/2, 8/3, right? Remember again what that's telling you is you would take 0 times the first vector, negative 1/2 times the second vector, 8/3 times the third vector. That's what that says. That's what the coordinates relative to a basis means. It's the coefficients on your linear combination. Your other one, coordinates will be 0, 1, 4/3. So then when you make your matrix, you're going to write these down as columns. So your matrix that goes, or your non-standard matrix for this transformation would be 0, negative 1/2, 8/3, and 0, 1, 4/3. To find the matrix, this is the process every time. Okay? Every single time. Let's look at the next one. Now notice in this case they actually gave us standard vector, so we've done one like this before. This asks us to compute this output in two ways. One way is to compute it directly. The other way is to use matrix multiplication. You should be able to do this directly, right? This says take x minus 3, plug it in for x, and then multiply the result by x. Right? All right, that's what this notation says. I'll write it down. I'm not gonna. If I have 1 plus x minus x squared, the notation says take x times 1 plus x minus 3 minus x minus 3 squared, right? It's function composition, right? Take out the x, put in x minus 3, multiply the result by x. Yeah? Okay, so when you do that, you would get a negative x cubed. You'd have a plus 6x, plus a 7x squared. This one would give you a plus minus 9 minus 3, and then times an x, so you get a minus 12x when you're done. If I did that correctly. It's the name of the function. It's just the name of the function, whatever the function is. The p is just the function name. I use p because I'm dealing with polynomials rather than f for function. All right. That would be one way to compute it, right, directly. The whole goal of this entire process, by the way, is that we're trying to get to the point where we can replace or compute any linear transformation as matrix multiplication. That's our whole goal here, all right? So let's do it the other way. The other way is compute the transformation on the output vector, or on the basis vectors for your input space. What do you get when you apply the transformation to 1? What do you get? You just get x, right? This says plug in x minus 3 for x. There aren't any, right? So p of x minus 3 is just 1 times the x, right? The next one would be x times x minus 3, right? Right? The transformation says take out the x, put in x minus 3, and multiply the result by x. Right? The next one would be x times x minus 3 squared, which would give you x cubed minus 6x squared plus 9x. Right? Again, take out the x, put in x minus 3 into the polynomial, and then multiply the result by x. That's what it says to do. Yes? No. I'm not splitting it up. I'm applying the transformations to the basis vector. I'm trying to create the matrix. Okay, so again, step one in creating your matrix is take the transformation and apply it to the basis vectors. What's step two? Find the coordinates relative to the base output basis, right? Here's your output basis. In that order, what are the coordinates? In the order that's given for B prime. Good. 0, 1, 0, 0. Again, in that order, the order is important here. It doesn't matter. The order doesn't matter as long as you're consistent. Okay, just make sure you pay attention to the order. What would this one be? Good. And the last one. Good. And then those are going to be the columns for your matrix, right? So your columns will be 0, 1, 0, 0, 0, negative 3, 1, 0, 0, 9, negative 6, 1. That'll be your matrix. Are we okay with how we created the matrix? To create the matrix is a two-step process each time. Find a transformation of your basis vectors, right? That's step one. And then find the coordinates relative to the output basis. Okay. Now it says to do this in two ways. Well, here's how we're going to do it. The coordinates of the output will be the product of the matrix we just found times your coordinate vector of your input. I'll write it this way, and we'll change it here in a second. Matrix times coordinate vector here, not B prime, that's a B. Sorry. The coordinates of your input vector relative to the input space. Okay. What are the coordinate vector? What is the coordinate vector in this case? Yeah, 1, 1, negative 1. And now let's multiply. What do you get when you multiply? Did I do that wrong? It should be 0 in the first one, right? Yeah, and 11 is not the right answer. So what did I do wrong here?
I think there was a mistake.
In this first part?
Yeah.
Okay.
If you get negative 3, you get a plus 1x, a negative 3x, and then or a negative 9x. So it should be negative 11.
It should be a negative 11. Oh, yeah, there is an x there. I forgot the x there. Thank you. I forgot the 1. There is an 11. Good. I forgot to add the 1. Whew. All right. Negative 11 here. What's the next one? 7. And the last one? Negative 1. Do those match your coordinates up here? Yeah. I knew there was an error somewhere. Those match up here. Okay. Knew there had to be an error because you should get the same answer. So again, these are the coordinates of your output. So then your T of, the final part would be your T of, oops, threw that across the room. 1 plus x minus x squared should be, in that order, negative 11x plus 7x squared minus x cubed, which is what we got. Again, that's the whole point of doing this, by the way. is to change the transformation into matrix multiplication. And again, the big theorem of this particular section is you can always do this for finite dimensional vector spaces. Every single transformation that you have for finite dimensional vector spaces can always be done through matrix multiplication. Every single one of them. So, for example, you can differentiate using matrix multiplication. You can integrate using matrix multiplication. Okay. All those things. So, we'll do more of this next week, and then we'll get into eigenvalues and eigenvectors, which is the last topic. I know Dayton's very excited about that. All right. Don't forget to email me if you haven't already about when you're going to take the exam. Okay. Make sure you shoot me an email. Let me know if you're going to come in at 8 on Friday, or the regular time on Friday at 8, or if you're going to schedule a different time on Monday. Okay? Have a good one.